Hey everybody, I'm Andy.
Hi, Andy.
So I work at NYU at the Center for Data Science, where I do a lot of work on scikit-learn. And I want to talk about large-scale nonlinear learning on a single CPU. And I'm going to start off by explaining what I mean by this. So for me, large scale here is out of core. That means data that fits into your hard disk, but not in RAM. So this ties beautifully into the desk talk for those that have been there. So to me, this is like 500 gigabyte to 5 terabyte. So 500 gigabyte, everything below just fits into RAM easily, obviously. And like 5 terabyte, and 5 terabytes, like what you can easily get on a hard disk. So I want nonlinear learning, which means not only like learning hyperplanes and high-dimensional spaces, because real-world problems are usually not linear. And I want to use a single CPU because parallelization across multiple CPUs is hard and often unnecessary and may make things slower, in particular in machine learning. So I'm talking mostly about machine learning here as a caveat. There was this very nice position paper here. Nobody ever got fired for using Hadoop on a cluster by Microsoft researchers. And unfortunately, so this is 3 years old. Unfortunately, this is still true. And a lot more people should get fired for using Hadoop on a cluster. Don't be the guy that doesn't get fired for it. Be the guy that works on a single machine and prototypes much, much faster and gets stuff working really, really quickly. And I'm going to tell you how to do that. So the beginning of my talk, this is the overview of my talk. In the beginning, I'm going to talk about at length why you should not do stuff on a cluster, and actually why you also shouldn't do the rest of my talk. That's also going to be completely useless. And then I'm going to tell you how to do out-of-core learning using scikit-learn, using some different methods like the hashing trick for text learning, kernel approximations, random neural networks, supervised feature extraction using random forest, and using actual neural networks. And then something about what else is out there. So, I mean, this main part will all be techniques for doing out-of-core learning, learning from disk. So actually, I don't think you should be learning from disk. Why shouldn't you be doing out-of-core learning? Because your data is actually not that big. Your data that you do machine learning on fits into RAM, believe me. So here are the costs from some not named cloud provider. So you can get this R3 8X large with 244 gigabyte of RAM for $3 per hour. That's much cheaper than a data scientist. That's also much cheaper than a backend engineer that sets up your Mesos, Spark, Hadoop thing, whatever you want. There's also the other thing that has 8 times 800 SSDs. So this is like 6 terabyte that you can get for $7 an hour. So this is you probably this one is okay for you, and you can just use scikit-learn and don't worry about what I'm going to talk the rest of the half hour. If you actually want to do this, get this one. It's slightly more expensive, and you don't actually have that much data. So I'm going to say 256 gigabyte ought to be enough for anybody for your machine learning. So who here has more than 256 gigabyte of data they want to do machine learning on? One person. OK, so the rest of you don't need this talk. Or I mean, OK, maybe you can do this, so then you can do a couple of gigabyte on your laptop where you maybe don't have that much RAM. But otherwise, if you have a lot of data, I'd argue just subsample. Throw away most of your data, then you can still do it in RAM. And if you have terabytes and terabytes of data, probably the result's going to be the same. In particular, if you have very imbalanced data. So if for every sample, if you do classification, for every sample in class 1, you have 100 samples of class 2, just get rid of 90 of the ones in class 2. You're still going to have all the interesting examples, which are the class 1 ones, and your result's going to be exactly the same. And you got rid of 9% of your data without any consequence. And that makes everything so much faster and easier. And it is. And this is not a very unrealistic setting. If you do things like ad-click prediction, no one ever clicks on ads. So you have imbalances of why would anyone click on a banner ad this day and age? Come on. So you have imbalances of 1 to 10,000, or I don't know, they don't give you the numbers. 1 to 1,000 or 1 to 10,000. And so you can throw away everything, basically. Like 1% or 0.01% of your data are actual clicks that you care about, and the rest is just everybody didn't click. And you don't need to actually use all of that. Anyhow, so if you subsampled and threw away your data and got the machine with lots of RAM, and you still want to do out-of-core learning, that's what the rest of this talk is going to be about. So obviously, I'm going to do it with scikit-learn because that's what I'm working on. So in general, the picture looks like this. You have your stuff, either your data on your hard drive, or maybe you're streaming in on your network. And then sort of what you need to do yourself is you write your own for loop or pulling that gets the data from the hard drive or network. And then you have some model that I call estimator here, and a bunch of these in scikit-learn have these partial fit methods. There's, actually, I don't have a list of these here. I think there's SGD classifier, there's naive Bayes, k-means, and a couple others. And this means that iteratively fit a model to a data chunk by chunk. So you take small bunches of data that fit into your RAM, and you fit your estimator, and you loop over these. And then in the end, you get out your trained model. Or maybe you do this continuously with data streaming in over the network, and every once in a while, you just take out the model that you currently have, and you test it, and you put it into production. So the simplest way you could do this is with a linear classifier. Here, I assume you have your data. You already chunked it up into like pickle files, or maybe it would be smarter to do it using Dask, or I don't know. So you have a bunch of pickle files. You load each of these. You instantiate your SGD classifier. The stochastic gradient descent is a linear learning machine. So we're not at the title with nonlinear yet. You instantiate it once. You iterate over all your files with your data. You get your X batch, which is the training data, Y batch, which is the training labels, and you call sgd.partialFit. And this way, you iteratively improve your model. You also have to tell it how many classes there are in your data set so that everything can be initialized correctly. So this is a binary classification task, and I keep putting in the data. So you can also use tools from Pandas. Pandas has a cool thing, an argument called chunk size. I think that's for tables, CSV files, and SQL, with which you can load batches of data from your disk. So if you have a very large CSV file, of course, why wouldn't you use anything else to store your huge data set? So you have, like, I don't know, a 500 gigabyte CSV file, and it doesn't fit into RAM. And you can use read CSV with a chunk size, and it'll give you chunks of data frames. And then you can iterate over all these chunks, get the features from your data, get your label, call partial fit on it, iterate over it. And so this way you can learn your machine learning model with arbitrarily large CSV files. One thing that you should keep in mind is for most of the models, like going back to the pickle version, you don't want to go over the data set only once. This way, your model would see each data point only once. It's probably not going to be good enough. And you need to iterate over the data set multiple times. So you do put in a for loop for a number of iterations. You load the batches, and you do load them and do partial fit. And maybe you want to randomize them, or maybe not. And you should do some monitoring to see when you should stop. All right, so that's for the sort of standard linear classification, but the title was nonlinear. So I want to go now into several options on how to do nonlinear or more advanced classification that is out of core. So the first option is to use what I call stateless transformers, which is some transformation of the data set that don't actually learn anything. They just map the data in some interesting way that you can then use for learning. The first one I want to talk about is for text data. And so, I don't know, who's familiar here with the bag of word representation? Okay, like maybe half, but more. So this is the standard approach to doing any kind of machine learning on text data, like classification, clustering, or something like that, to get a string, like this is how you get ants, into a vector representation that you can use in your machine learning algorithm. And it goes like this. So you start with your string, you tokenize it. The easiest way to do this is, so you split it up into words. The easiest way to do this is use a regexp and just split on white space. And we also normalize it a bit by lowercasing it. You could also do something much more advanced, but just say we split it up and lowercase it. Then we build a vocabulary over the whole data set we have, over the whole corpus of all the things we want to learn from. And then using this vocabulary, we do sparse matrix encoding. We say, how often does the first word in dictionary appear? Aardweg, 0. Amsterdam, 0. And then there's a whole bunch of 0, and at some point there's ants. And there's one ants appears once. So that you have this huge vector. The length is the number of words in your dictionary, and it has very few entries that have a 1 there if the word appeared once. Or maybe the word appeared 10 times and there's a 10. And we can use the sparse matrix representation to only represent the numbers that, or the words that actually appear. The problem here is if we have a large data set that doesn't fit into RAM, then first, so to build the vocabulary, we need to iterate over the whole data set. And maybe if we're in a streaming setting, we can't do that. Also, the vocabulary will be huge if your data set is huge. So you might not be able to store this into RAM. So there's some problems with scalability here. But there's a cool thing called the hashing trick to kind of get rid of the vocabulary. You start off the same way. You start with a string, you tokenize it. But then instead of building a vocabulary, you just hash each string. We use like a murmur hash function. So you go from the string this to some more or less arbitrary integer. So here, 832,412. And you do this for each of the tokens. And you do mod some very large number. I think we do some 10 to the 20 or something. So you get a very large number for each word. And this is completely independent of all the other words that might be out there in the world. So you just get an integer. And then you can use this for sparse matrix encoding without ever building a vocabulary. So you just use this number as an index into your sparse matrix. Downsides of this is you can't go back. So once you have your feature representation, you don't know which word O1 corresponds to because you can't invert the hash. The other kind of downside is you could get collisions, or you will get collisions. If you have more words than there's space in your hashing output space, then words collide. In practice, this is never a problem because the hashing space is large enough. And if you do machine learning, only few of the words will actually matter. So it's unlikely that two words that matter collide. So this is a pretty awesome thing to do large-scale text classification. It looks like this in scikit-learn. So I am applying the SGD classifier. So this is like, again, linear classifier. It's Hinchler, so it's like a linear SVM. And instantiate the hashing vectorizer. I load my data from pickles. So now I assume it's text batches. So maybe I should have used text files. I don't know. So I load all my text together with the labels. Then I transform my data using the hashing vectorizer. I get out X batch. So I just call transform. There's no fit here because it's like a stateless transformer. Hashing vectorizer doesn't need to be fit to any data. It just transforms the data using the hashing trick. I get out my X batch, and I can train my linear model on that. So this was for text. So let's say you already have some float features. One of my favorite ways to do out-of-core nonlinear classification is kernel approximation. The idea of kernel approximation is, I don't want to go to the math, but to do something like a nonlinear SVM, but you want to make it scale more. So usually nonlinear SVMs, you need to have everything in RAM. Also, it's very slow. Here the idea is to do a feature transformation of your data so that the inner product in the target space approximates the kernel. So here we have this RBF sampler that approximates the radial basis function kernel in a kernel SVM. There's a kernel parameter gamma that we set, and then we say it's actually 400, so I want 400 components. So it's going to generate 400 like random features that approximate the RBF kernel. And this is, again, this is stateless, so it doesn't learn anything about the data. It's just a transformation that's kind of cool for machine learning. I have to call fit here to tell it how many features I have. So I just fit it with a dummy data point that has the right number of features. Then again, I iterate over my data set. I call transform on my data. I get out like the kernel approximation version of the data. I call xkernel, feed it into my linear classifier, and I'm happy. And now I learned a kernel SVM on a streaming data set. So that works, and it's quite fast, and it works well. Another kind of similar approach is not using this kernel approximation, but using random neural nets. The idea here is that you do want to train a neural network, but you actually only fit the last layer. So you do like a 2-layer neural network, but the first layer is just you initialize randomly. There's nonlinearity, and you just keep this nonlinearity and the random weights, and then you do a linear classifier or linear regression on top of that. And this first layer, that's just a random matrix multiplication, then a sigmoid or a tanh H is implemented in the random basis function. And so that's actually not merged yet, but it's going to be there soon. It's also very easy to implement yourself. But the idea is basically you do a large nonlinear projection of your data. This was popularized as extreme learning machines. Then it turned out people who popularized it are complete frauds, so we're not going to call this anymore extreme learning machines. But it's still useful. So it's actually like the math is very similar to the kernel approximation, only it doesn't approximate anything. It just makes your data be nonlinear transformed. But it works. It's fast. So that's stateless transformers. Second option is learn transformations on a subset. So now I want to have a stateful transformation. I learned something from the data, but because I want to learn something interesting, but my data doesn't fit into RAM, so I'm going to use a subset. So I start off by loading my subset that fits into RAM. And on this subset that is like small, like 200 gigabyte, I train a random forest classifier. So this is like a very powerful machine learning model. Then I want to use this random forest to transform my data in some interesting way. The way I do this is, if I train a random forest classifier, it's a bunch of decision trees. So if I put in a new data point, it'll land, for each tree, it'll land in one of the leaves of the decision tree. And if I call this rf.apply method, it'll give me, for each tree in the forest, it will give me an integer that says which leaf they land up in. And this gives me a lot of information about this data point, because the structure of the tree reflects sort of information about the labels. That's how the trees are built. Then I can use a one-hot encoder and transform all these integers into like a large binary vector. So it'll have as many entries as there's leaves in the whole tree. Leaves in the whole forest. And there's going to be a single non-zero entry, that's the 1, for each tree. So this is like a huge sparse feature representation that uses label information from my subset. So this is like a complex thing, and I encapsulated the knowledge about the subset in this complex learning machine. And then I have a nonlinear feature transformation, this binary vector, and on top of that, I learn again my linear classifier. You can think of this as rebalancing the counts of different classes in each leaf. So, and doing this, applying a random forest and learning a linear classifier is very fast again. So this is a method similar to this was used in Facebook ad click prediction. They published a paper on it, so that's probably not what they're doing now anymore, because then they wouldn't have published it. But they used gradient boosted trees that they could build like overnight, and that took a long time. And then they used a linear classifier on top in a way similar to this, that they could update like instantaneously every 2 minutes to react to new trends. So this is like, you can easily do this in a streaming setting, but you can't really build a random forest in a streaming setting. Okay, so that's kind of cool. And the third option I want to talk about is the obvious option. Just use an online nonlinear classifier. Don't use your linear classifier or some transformation. Just use an online linear classifier. For example, use a multi-layer perceptron in a neural network. So unfortunately, that's also not merged yet. So instead of doing SGD classifier, linear model, linear SVM, we just replace this with MLP classifier, multi-layer perceptron. And should work the same way. You fit your neural network, and then you get a nonlinear classifier. Only downside is it'll take forever. And so you maybe, yeah. So they will be in scikit-learn pretty soon, but they will be on CPU. And maybe you would rather want to do that on a GPU, and it's still going to take forever. So just not doing the random projection and not training a lower layer or doing the random forest thing, all of these will be much faster and much easier to implement and probably less hassle. This will probably give you better results. Maybe. If you have enough data and if you're patient. Okay. So the last thing I want to talk about is what else is out there. So if you want to do out-of-core learning and you have a lot of data, you should really look into Vopal Webbit. which is a C++ project with a command line interface that's interesting. C++ code. Don't look at it. Also hard to pronounce name. It's a great library though. And so they do a lot of online learning, linear, nonlinear, deep nets, hashing stuff, extract features, learn features. They're like super fast. So I went in their code. So people are interested in topic models are probably next door, but they have topic model code in there. And then there's like, they re-implement like this Quake square root approximation where you XOR the bits. Okay, they're crazy people. Awesome stuff. They also have some cluster stuff. You should also look more into deep learning if you actually want to use one GPU and you have like weeks and weeks to spare. Then there's, for Python in particular, there's Keras and Lasagna out there, which are very good libraries. Or if you're more masochistic and have more time, you can use Cyano directly. There's also Hogwild, which is if you don't want to use a single core. So the things that I showed you was a single for loop training one linear classifier, which is actually pretty good often. You can also do this in parallel on multiple parts of your data, on multiple processors, and just forget to lock the weight vector. That's basically what Hogwild does. Everybody just updates multiple threads, accessing the weight vector and updating it in parallel, and it works. And they have some math that shows that it works. So that's pretty cool if you want to do multi-core stuff. Oh, so also, I think I said it before. Center for Data Science, NYU is hiring people to do open source full-time. That's anything that's data science related and open source. We'll pay you a full-time, like industry level salary for that. For some reason, no one wants to do that. I don't know. Anyhow, also, yeah. So thank you. Talk to me if you still think you need a cluster for machine learning. And there's going to be machine learning birds of a feather with me and Kyle now, where you can scream at me or tell me why scikit-learn sucks. And that's it.
Woo! So the example, you balance classes from the beginning of the presentation.
Yes.
You get one positive class every 100 negative classes. You subsample down to 10 positive or 10 negative classes. Why 10? Why not 5?
Cross-validate. In particular, for subsampling, I would say like subsample more than you think you should, and then compare against subsampling as much. So I mean, it's easy for you to subsample more and see if it makes it worse, right? And if I subsample it 1 to 1 and then 1 to 2 and they're both the same way, then probably 1 to 1 is fine. So the gamma is like a parameter of the RBF kernel. So if you train a nonlinear SVM, you just have to come up with that, like cross-validate or something.
And that's cool. You can just kind of you can cross-validate on a bunch of data and just focus on what's in every batch.
Yeah, there's no support. There's no built-in support for grid search for out-of-core learning in scikit-learn at the moment. So you can't generate a pipeline with this. There's no out-of-core pipelines in scikit-learn. So I'm going to talk with the desk people. Maybe we're going to make that soon. But yeah, but it's easy to implement. Like, okay, you can do these batches are my holdout batches. These batches are my training batches, and then I do a for loop over all the gamma values. That would be my advice so far. Yeah, so I think it kind of depends. I mean, it depends on the algorithm first. So let's say we just want to do linear classification. That's then their I/O is crazy. So also they have their own I/O caching. So if you iterate over the same batches multiple times, so here what I showed is you would load the pickle from disk multiple times. This will totally kill our performance. So they load the data and then store it into some crazy compressed format and like have some cache eviction strategy and stuff. So if you reuse the data, which you probably should, then their I/O will be better, and that will make them faster. In terms of the actual updates for linear SGD, I don't think it makes a difference. Probably, maybe they're slightly faster. Got us up. You can ask me more questions in your birth of a feather.